we're going to talk about section 3.7 problems of motion. So this is all going to concern actual objects that are going to move. And so we're going to talk about what we know based on the information that they give us. So usually they're going to start at least for now, that they're going to give you one of the functions. Most likely they're going to give you what's called the position function. So this is where an object is. So physically, it is at this spot. Usually, you'll see it listed as S of t, but it could be, could be something like X of t or something similar. You never know what kind of symbol they're going to use to describe it. But that's the where. Um, After that, we know that if we're given that function, we can actually find using the derivative the next function, which is our velocity function. So the velocity function you usually see as v of t. Now, the cool thing about that, again, is it's the derivative of the position function. So all we have to do is take the derivative and we get our velocity function. Now, our velocity function is telling us kind of, how fast we're going, right? And so not only does it tell us kind of the speed, but it also says which direction we're moving. So kind of like when we did our first derivative test, we knew whether we were increasing or decreasing. Now we can figure out which direction our object is moving. Very, very similar. Our last part is we have what's called our acceleration function. Now, acceleration, you're usually going to see as a of t. Now, the nice thing about that is our acceleration is our derivative of our velocity function, which in turn is also the same thing as the second derivative of our position function. So it's kind of a ladder, right? And we're going to be able to move backwards or down the ladder now, but we're going to be able to move up the ladder later. So going from acceleration to position. Right now, we can only move down. Right? We're not allowed to go up yet, but we'll work on that last semester. So your acceleration kind of tells you, how fast everything is changing with relation to your velocity. So am I speeding up or am I slowing down? So all of these things can tell us a lot about what's happening. Now, the really kind of important parts to this are that these are going to almost always be word problems, and they're going to list different things. And so I'm going to go through a couple of problems with you that's going to kind of explain how to interpret some of these different parts. But first, before we get to that, I'll explain certain things that we may know. Okay, so let's say, for instance, it tells me that, at time 3 seconds, what that implies is that time is 3, right? So we know that we can convert that piece of information into something else. So, we could also say that, if my object is at rest, you see this a lot. So when an object's at rest, that only tells me one thing, really, and that tells me that my velocity function is equal to 0. So we don't know the time, but we know that I'm not moving. So I'm not changing my position, right? And so my velocity is going to be at 0. That's one that they use quite often. You can also see things like, when the acceleration is 0, but these are the most often kind of wordings that you need to be able to interpret. So let's look at a problem. So it tells us that we've got s of t equals 3t squared plus 5t plus 2, describes a particle's motion with its units in meters. So it wants us to find the velocity and acceleration functions. And then it wants us to find the instantaneous velocity and acceleration at time t equals 4 seconds. So we start off with part A, and it says for us to find the velocity function. So remember, my velocity function is the same thing as the derivative of my position function. So all I need to do is find the derivative of my position function. So if I go up here, it's a pretty simple one to deal with. So I've got 3t squared. The derivative of that is going to be 6t. And the derivative of 5t is going to be 5. And the derivative of 2 is 0. So I don't have to do anything there. My acceleration function, again, that's equal to the derivative of my velocity function, which I've already solved for. So it's just the derivative of what I'm seeing right above. And so the derivative of that is simply, it's not 5t, it's just 5. Apologies. And so the derivative of 6t plus 5 is just 6. So that's it, right? This object is always accelerating at 6. So you see that often, like you know, things that are constantly accelerating are pretty much objects on Earth. We always accelerate down. This is actually accelerating up, so it's kind of interesting. So part B asks us to figure out what's the instantaneous velocity and acceleration at time t equals 4. So what it wants to know is, what's the velocity when t equals 4? Well, we go and we have our velocity function, and we plug 4 in. Well, the velocity function is just 6t plus 5, so I do 6 times 4 plus 5, which is going to equal 24 plus 5, or equals 29. Now, because I'm doing velocity and this is in terms of meters, and I'm talking about seconds, this is going to be meters per second. When I'm asked to do my acceleration at time 4, well, it's always 6. And when we do this, we're taking meters and dividing by seconds, and then we divide by seconds again. So it's meters per second per second. Or more commonly, what you're going to see is it's going to be 6 meters per second squared. But that's normally how you see the physics problems listed. Now, let's look at another problem, kind of similar, but we're going to be given some different types of information. So we've got a particle, it moves along a path with its position function being t squared minus 6t plus 8 meters. When does the velocity equal 30 meters per second? So what we're trying to figure out for A, what we need to figure out is, when does the velocity, so keyword when, so that means that we're trying to figure out a time. We need to figure out what time this is happening. And so when the velocity equals 30 meters per second. So what we're really looking for is our time, t, when the velocity equals 30 meters per second. So what we have to figure out is, how do we get to velocity given the information we have? Well, we have our position function. Our position function is t squared minus 6t plus 8. So we do know that our velocity function is going to equal the derivative of our position function. So the derivative of our position function here is the derivative of p, which is going to be 2t minus 6. So I want to figure out what time does this happen. Okay, so when I go back and I say, okay, so v of t equals, excuse me, 2 t's, right, minus 6, and that's going to equal 30. So at this point, we've got the equation that I'm supposed to use. So I know that if I use this equation, I can find that 2 t's are going to equal 36, and therefore I'm going to have t is going to equal 18. Now, this is 18 seconds. So after 18 seconds, I'm going to have a velocity that's going to be equal to 30 meters per second. Okay, and part B says, when is the particle at rest? So remember, we talked about that before. When it says that the particle's at rest, that implies that, and again, it's asking when. It's saying, when does my velocity function equal 0? Okay, so we've got our velocity function already. So we know that my velocity function is equal to 2t minus 6. Okay, so all I need to do is solve for that. So you should end up with 2 t's equaling 6, and simply t is going to equal 3 seconds. So these are types of problems you'll see. Now, some of them vary quite a lot. Sometimes you'll see graphs, sometimes you'll see other things, but mainly what you want to focus on is figuring out what function does it give you, what is it asking of you, and what does that mean? Because sometimes we'll be solving for time, sometimes we'll be solving for what the velocity is at a certain time. But we always need these pieces of information in order to move forward with these types of problems.